Hey everyone, Houston Math Prep here. We are starting our series of solving exponential equations. In this video, we're just doing part one, where we have like bases, similar bases for exponentials on both sides of the equation. If you look at our first problem here, I have 2 to the x plus 3 equals 2 to the x minus 1. Just a little tidbit about why we're going to solve these the way we're going to solve them. If you looked at our videos on graphing exponentials and figured out whether or not they have an inverse, we figured out that exponential functions pass the horizontal line test. They're what we call one-to-one, and they have an inverse. So if I have an exponential function equals another exponential function, the idea is we're never ever going to hit the same y value twice. So when I have 2 to the x plus 3 equals 2 to the 2x minus 1, the graphs of these are only going to intersect each other when these exponents are the same. So to solve these, we can simply think about setting x plus 3 equal to 2x minus 1 because these are the same base. So we just solve exponents equal to each other. X plus 3 equals 2x minus 1, and this looks like a much easier problem to solve, right? So if I go ahead and get all my x's together on one side, combine my x terms, then that will leave me with 3 is equal to just x minus 1. And then I would need to add 1 to both sides to get x by itself. And then we would get that 4 is equal to x, and that would be our answer. So just remember, when we have an exponential equals another exponential, and they're the same base on either side of the equation, and that's all we have, then we can just take the exponents and set them equal to one another and solve those. Let's look here at 7 to the x minus 2 equals 49. Now, you might just be able to look at this and see it, but let's keep with our method here. The difference with this one, though, is I don't have an exponential equals an exponential. But what I should probably notice is that 49 is definitely a power of 7, and it's almost certainly a power that you know off the top of your head, right? So if I think of this as a power of 7, then I could have an exponential base 7 on both sides. In other words, if I have 7 to the x minus 2 equals 49, and think of 49 as 7 squared, now I have an exponential with base 7 on both sides, and I can think about taking these exponents and setting them equal to each other. So in other words, x minus 2 must equal the number 2. This is really easy to solve if we see it this way, because we just need to add 2 to both sides, and that will give us, in this one also, it turns out, x equal to 4 for our answer. Looking at another one similar to that, 5 to the x plus 1 equals 25. This is not an exponential, but it is a power of 5 that we are most certainly aware of. So I can think of this as 5 to the x plus 1 equals 5 squared. 25 is 5 squared. And now that these are exponential equal exponential with the same base, I can set these exponents equal to each other, and I can simply solve x plus 1 is equal to 2. I subtract 1 to solve this. Subtracting 1 from both sides will give us that x equals 1 for our answer here. Here's another one, 3 to the x minus 4 equals 1/9. What we want to see is that 1/9 is a power of 3. So if you think about 3 squared is just plain old 9, this is the reciprocal of 9. So we know that powers of exponents, if we want a reciprocal, we need a negative exponent, right? So we want to think of 3 to the negative 2 is 1/9. So if we think of this as an exponential instead of just a fraction and change that, then we have the same base, right? So 3 to the x minus 4 are 1/9. Let's write it as 3 to the negative 2. And now with base 3 exponentials on either side, we can set these equal to each other. So we can say x minus 4 is equal to negative 2, and we just simply need to add 4 then to both sides to solve this. And we will get that x equals positive 2 for this equation. Looking at this one, 6 to the x equals 36 to the x minus 1. Now here I do have exponentials on both sides. The problem though is that they're not the same base, but they are like bases. What we'll do is think of our 36 as a power of 6, right? This is base 6, but I could think of 36 as a base of 6. The only difference here is this one also has an exponent, so we just have to make sure and hang on to this x minus 1 exponent. So let's go ahead and keep our base 6, so we'll say 6 to the x on the left side. And I want to think of 36 as 6 squared. So just change the base for now and just say 36 is 6 squared. And I'm going to write it in parentheses to help you think about it. Now, we still have to the power x minus 1, right? So the question then becomes, what do we do when we have an exponent outside of another exponent? And if you remember your properties of exponents, we multiply these exponents together. So let's go ahead and say 6 to the x is equal to, now we'll need to multiply these. Don't forget to distribute your 2, right? Because we have more than one term there multiplying. So we'll have 6 to the 2x minus 2 on the right-hand side. Now that we have exponentials that are the same base on either side of the equation, we can just set their exponents equal to each other. So I will get x equal to 2x minus 2. If I go ahead and get my x terms together, let's say I subtract 2x from both sides, that will give us that negative x is equal to negative 2. And if I divide both sides by negative 1 or multiply by negative 1, then that will give me that x equals 2 for my answer. Okay, so just because you have two exponentials with different bases doesn't mean that you can't solve them just by sort of manipulating them to become the same base. Let's look at another one like that. Here I have 4 to the x equals 8 to the x plus 1. The problem with this one is that 8 is not just some nice round power of 4 that I know, right? 4 to the 1 is 4, but then 4 squared is already 16. It's bigger than 8. So I don't know maybe in my head what power of 4 8 is. What I can do though is change both 4 and 8 into easy powers of something else. And if you stare at these numbers for a second, you might notice that 4 and 8 are both powers of 2. So we're going to actually change these into base 2. So I want to think of 4 to the x. I want to think of my base as 2 squared. I'll still have to the x. And I want to think of my 8 as 2 to the third, right? 2 cubed. And of course, I still have my x plus 1 exponent out there. Now these will all be in terms of base 2. So if we use our properties of exponents and multiply now, I get 2 to the 2x on the left side. And don't forget to distribute your 3 into each piece here. We will get 2 to the 3x plus 3. Now that they're both base 2 exponentials, I can set the exponents equal to each other. So we will get that 2x is equal to 3x plus 3. And if I subtract 3x from both sides, I will get negative x is equal to 3. And if I divide both sides by negative 1, then we'll get that x is negative 3 for this one. Looking here, we have 27 to the x minus 1 equals 9 to the x plus 5. This is a similar thing. Powers of 9, I know 81 is a power of 9, but 27 is not a power of 9 that I might know off the top of my head. So think about, could I make these a similar base, but maybe not 9 or 27? And if you look at 9 and 27 for a second, you might realize that these are both powers of 3. If you think 27 as a power of 3, that's actually 3 cubed. 3 to the third power is 27. So this side will be 3 to the third to the x minus 1. And this side here, thinking of 9 as a power of 3, that will be 3 squared, and then to the power x plus 5. Now, when you distribute, make sure you distribute each piece. So this will become 3 to the 3x minus 3, right? 3 times x, 3 times negative 1. And then over here, we will get 3 to the power 2x plus 10. 3 to the 2x plus 10. And now that they are both base 3 exponentials, we can set these exponents equal to one another and solve. So we'll solve 3x minus 3 equals 2x plus 10. I will go ahead and subtract 2x from both sides, combining my x terms. That will give me x minus 3 is equal to 10. And then I can simply get rid of my minus 3 with adding 3 to both sides. And we'll get x equals 13 for this one. Let's look at one more. I have 2 to the x squared, so I have x squared as a power. That's a little different, right? Equals 16 to the x. 2 and 16 are not the same base, but 16 is a power of 2, so let's go ahead and change that. So we'll keep this as base 2, and we'll say 2 to the x squared. Interesting power there, right? We want to think of 16 as 2 to the 4th power. So that'll be 2 to the 4th to the x. Let's go ahead and do our multiply with our exponents here. So that will give us 2 to the x squared equals 2 to the 4x. Now that we're both sides base 2 exponential, I can set the exponents equal to each other. When I do that, I get x squared equals 4x. Now this is not just a linear equation like all our other ones, right? This is a quadratic equation. So our options are square root, factor, use quadratic formula, complete the square. I think this is a nice one for factoring. What we don't want to do is divide by x on both sides because we're going to lose one of our answers. So if I get everything on the same side, maybe I subtract my 4x over to the other side, and I say that x squared minus 4x is equal to 0. You'll notice we're going to get two solutions here for this one, because if I factor the common factor of x out, I get x times x minus 4 is equal to 0. And remember, when we solve by factoring, we then set each factor equal to 0 once we have our list of factors multiplying to get 0. We have x equals 0 and x minus 4 equals 0. This one's already solved, so 0 is one of our answers. This one we do need to add 4 to get our second answer of x equals 4. So 0 and 4 for this one. Okay, that's our solving equations part 1 with like bases, being able to make the bases match if they don't already match in some way. Thanks for watching, everybody. We'll see you in our part 2 video.